Okay, our next speaker is Andrés Vindas Meléndez, and he will talk about triangulations, order polytopes, and generalized snake posets.
Awesome. Hold on, let me just smile for the picture because it's distracting afterwards. Yeah, thank you all for being here on the last day. I think we should all just like shake our arms a little bit because I noticed that you all were falling asleep at some point, and I don't want you to fall asleep in my talk. Yeah, so first I would like the organizing team and all the volunteers and helpers, the people running, giving mic and like handing the microphones to stand up so that we can acknowledge you and actually see you. So please, organizing team and everybody else, stand up. The volunteers, I know that you all are here. Don't be shy. Awesome. Thank you all so much for everything that you've done, and for opening a space for us and your academic institution. Yeah, so I was preparing this talk and I was like, man, I don't know what to say, what kind of jokes to say to keep everybody engaged. And so I didn't think of any jokes, but life is sometimes a joke. And so yesterday, well, one, I was hoping that we would have music at the banquet, but it didn't happen thanks to somebody on the first row in this area. And so hopefully if you're interested and you're local, you should take me out to drink some beer or wine later on, and hopefully there'll be music. But when we got back from the banquet, I was walking home, and I apologize to everybody that I walked past and I did not interact with you. The universe is funny, and a bird pooped on me, and I'm not going to say where it pooped on me, but where I'm from, that is good luck. So here's to a good talk, a healthy, successful math career, and a long, healthy life. So let me get started with the triangulations, order polytopes, and generalized snake posets. So I also just need a feel of who's in the audience, because I've met a lot of you, but I don't know everybody. So undergraduates, wonderful, welcome. Graduate students, great. Postdocs, established or seasoned mathematicians. Okay, yeah, great. Welcome. Okay. So I'm going to ask another thing. Who here has never heard anything in my title? It's okay to be honest. We're friends here. We spent all week. Some of us got COVID together. Okay. So who knows one thing? At least one thing, okay. Who knows at least two things? Okay, good. Who knows all of the things? Okay, well then you're gonna answer all the questions because my collaborators are not here to do that. Okay, so first I'd like to, acknowledge my collaborators, the team. So I was very fortunate to have done my PhD at the University of Kentucky, which is now a very combinatorics powerhouse because it has a big combinatorics group. And so here we have Matthias von Bell, who's moving to TU Graz as a postdoc, Ben Braun, who is my PhD advisor, Jared Cayley, who's starting as an assistant professor at Penn State Barron, Christina Serienko, who's a professor at Kentucky, Julie Vega, who left higher education, is going to be teaching at a merit school, which is an independent public school or private school, and then me, and then Martha Yep, who's a professor at University of Kentucky. So somebody caught my slides while I was preparing and stuff, and they're like, wow, there's 7 people on this thing. For me, it brings me great joy to work with a lot of people, and this is a wonderful group of mathematicians that I've had the privilege of working with. Okay, so order polytopes. Okay, so we're going to let P be a partially ordered set on the set of elements 1 through D. Okay, and so an order polytope is a polytope defined as the set of points satisfying these inequalities, xi is less than xj for I and j in the poset. Okay, so maybe some of you haven't seen polytopes before. I always like to say that let's think about them in 3 dimensions and throwing points into 3 space and then saran wrapping them, or wrapping them with that like plastic that you wrap your luggages in the airport, right? So it creates a shape that's very flat and has flat sides. Yeah, and so then you might say, well, that is just a definition. Where's your example, Andres? And so here's an example. I'm going to let P be the diamond poset. Okay, so what is this? This is saying 1 is bigger than 2, 1 is bigger than 3, 2 is bigger than 4, 3 is bigger than 4, but there's no relation between 2 and 3. Okay, everybody with me? Okay, great. So here we're defining, we look at the six upper order ideals. And I want to make sure everybody is on the same page. So an upper order ideal is a subset of P such that if an element I is less than J, then J is in A or is in that subset. So let's look at this one as an example. 2 is less than 1, right? And so if 2 is in our set or subset and 2 is less than something, it's less than 1, then 1 is also in this subset. Okay. Nothing too crazy so far. Okay. And so from that poset, now I create my polytope, which is this order polytope. And I should have said that order polytopes were popularized by Richard Stanley in 1986, which is with his paper on 2 poset polytopes. But in that paper, he writes that order polytopes, the literature is scattered everywhere. So I actually don't know who to attribute order polytopes to. So, but most people attribute it to Stanley. And so from the 6 upper order ideals of this poset, I take the indicator vector, and so I create some points in n space. Yeah. In this case, it's a 4-dimensional thing. So the empty set is this 0, 0, 0, and then there's this 1, 1, 0, 0, and then 1, 2, 1, 1, 0, 0. Okay, and so on. Okay. Everybody okay? Awesome. Okay. And so then this is oops, my fingers are too big. This is the polytope that we get. And of course, this is a Schlegel diagram in 3 dimensions because this is a 4-dimensional polytope. Okay. So what do we know about the order polytopes? Well, the dimension of an order polytope is the number of elements of the poset. The vertices correspond to the filters of the poset, or the upper order ideals. The volume of the order polytope is the number of linear extensions of the poset. Okay, so there's some algebra, combinatorial thing giving us some geometric information. Okay. And so that's order polytopes. So the title of my talk is Triangulations, Order Polytopes, Generalized Snake Posets. So we covered the middle one, order polytopes. And so now generalized snake posets. Sorry, yeah, that's a great question. I should say this is normalized volume. So it's Euclidean volume times dimension factorial. Yeah, so we want to normalize it so that we have an integer. Yeah, great question, great point. Okay, so generalized snake posets. So for n non-negative integer, we define a generalized snake word as a word W0 through Wn, where W0 is the empty letter, and Wi is in the alphabet LR for I 1 through n. And so the length of the word is n, which is the number of letters L or R. Okay. And so from there, from this generalized snake word, we're going to define the generalized snake poset. So given a generalized snake snake word, we define the generalized snake poset in a recursive way. I didn't want to write the whole definition, so here I'll give you some pictures. Here's what we're calling the snake poset, which is the poset from the empty letter left, right, left, right, left, right. So that's why it's a snake, because, well, it looks kind of like a snake, so my co-author said. Okay, everybody okay? Yeah. Okay. And then here we have the ladder poset because it looks like a ladder. So just the empty word L, 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 L. Nothing too crazy. Yeah. Okay. Everybody with me? Okay. So what do we do with polytopes? Well, one natural question is to ask for its volume or its normalized volume. Okay. And so here's our first theorem. For n greater than 0, we let W be a generalized snake word. If k is greater than or equal to 0, if k is the largest index such that W sub k is not equal to W sub n, then the normalized volume of our order polytope is given recursively like this, by this formula. Okay, so it's nice and to me because Catalan numbers, and everybody loves Catalan numbers. Okay, and so from there, we get a corollary. And so we can write down the normalized volume for the order polytope of a snake poset. Okay. And so in this recursive way. And if you are familiar with this, you might recognize them as the Pell numbers. Okay. And then we also get another corollary for the order polytope of the ladder poset, which is this Catalan number. And this result is actually hidden in these two papers. In these two papers, because both of these papers talk about flow polytopes. Okay, and so flow polytopes are integrally equivalent to order polytopes if you take the Posset diagram to be a strongly planar graph. Okay, and if you don't know about flow polytopes, don't worry. Here's the nice results about the volume of order polytopes, which you're all now familiar with. Okay. And I should say one other thing here. This is what is the flow polytope? If you actually do know the literature, if you want to talk about it, this is this paper by Benedetti et al. That talks about the flow polytopes of these graphs called caracol graphs or snail graphs. And this is the volume that they compute, but they don't phrase it in the language of order polytopes. Okay. And so another theorem is that for any generalized snake word of length n, we have this inequality. So for fixed, size, the volume of the order polytope of the snake poset is less than or equal to the volume of the order polytope of the the poset coming from this generalized snake word is less than or equal than the volume of the order polytope of the ladder. So what did we do is we characterize what's the smallest and what's the biggest, and so anything can happen in between. Yeah. Yes. So the question is, shouldn't the ladder have the least number of linear extensions? I don't think so. Yeah, I don't think so. Yeah, because then this would definitely not work. Yeah. So I don't think so. But we can double check and make sure that this is right. Okay, so let me pause here because now I've done order polytopes, and I presented to you generalized snake posets, and now let me introduce or bring in triangulations. Okay, so triangulations, if you've never seen them formally, you have at some point maybe seen them, and it's exactly what you might have in mind. So you consider a polytope in D space. A triangulation is a subdivision of the polytope into D simplices, so simplices of dimension D. Okay, and one nice type of triangulation is a triangulation that is unimodular. Okay, so a triangulation is unimodular if every simplex has normalized volume 1. Again, normalized volume is Euclidean volume times the dimension factorial. Okay, and why might that be nice? Sampa, why is that nice? Why are simplices nice? I'm putting Sampa on the spot because I put her on the spot the other day too. So in the spirit of Sarah's definition of combinatorics, saying that that combinatorics is the nanotechnology of math, simplices are the nanotechnology of polytopes. Okay, so you can build anything from a simplex, and if you have a unimodular triangulation and they all have normalized volume 1, then all you do is count the number of simplices and you get its normalized volume. Okay, so I mean, at least that's one reason why we might care. Okay, but not every triangulation is unimodular, or not every polytope has a unimodular triangulation. And so the second kind of nice triangulations that we care about is a triangulation that is regular. So a regular triangulation is a triangulation that can be obtained by projecting the lower envelope of a lifting of the polytope from one dimension higher. Okay. And so here are some examples. This is a picture I took from this nice paper by Posets et al. On existence of unimodular triangulations. And so these two are unimodular triangulations because you can see that the simplices all have normalized volume 1, and this one is not, because this one has an interior point, and a property of a unimodular simplex is that it does not contain any interior points. Okay. And here's a picture depicting this projecting the lower envelope of the lifting of the polytope. So the polytope is this one. You take some height function, lift all the points, and then you project down, and whatever kind of shadow you get is this is a triangulation. It's a regular triangulation. And so I think it's the case that every polytope has a regular triangulation, but it might be difficult to find, okay? And it's like the best thing ever if we can have a regular unimodular triangulation. Okay, so triangulations of order polytopes. So what is known about triangulations of order polytopes? So, well, first, let me define to you something before that. So this is what Stanley did. So Stanley took this hyperplane arrangement. Who recognizes this hyperplane arrangement? Yeah, a lot of people should recognize it. So this is the type A braid arrangement. So Stanley took the type A braid arrangement and said that this hyperplane arrangement induces a triangulation on the order polytope. And this is known as the canonical triangulation. Okay, and it has these following three fundamental properties. So the triangulation is unimodular, so we're good. The next thing is that he showed what I already mentioned is that these maximal simplices are in bijection with linear extensions. So the normalized volume of the order polytope is the number of linear extensions of the poset. Okay, and the last thing is that he gave us exactly how to construct the simplices. From these linear extensions. So each linear extension gives us one simplex in this triangulation, one unimodular simplex, okay? So what has been studied in terms of triangulations of order polytopes? So order polytopes, have been studied for quite some time now, but what about their triangulations? So for graded posets, this is work done, triangulations of graded poset or order polytopes of graded posets have been studied by Reiner and Velker. Non-unimodular triangulations related to graph associatetra has been studied by Ferre and Reiner. Products of change has been studied by Santos, Stumpf, and Velker. And S-lecture hall order polytopes has been studied by Brandon and Solis quite recently. And then we also know things about disjoint unions of chains. Okay, so we have kind of a lot of examples of triangulations of order polytopes, but I don't think any of them use very, similar techniques. It kind of really does depend on the posets and so. But if this is of interest, you can go and look at this, okay? But now what I want to kind of shift gears is the space of regular triangulations coming from these posets hasn't been studied as much, okay? And so what I'm gonna do next is define the flip graph of the polytope. So the flip graph is a graph where each triangulation corresponds to a vertex in the graph, and a flip from a triangulation to another corresponds to an edge. And then you should ask, Andrés, what is a flip? And so I didn't write it down. So a flip is a local change that transforms one triangulation to another. And so flips happen on what we call circuits, and circuits are minimally affine or affinely minimal dependent subsets of the vertices. Okay, and so they're happening on a subset of the vertices, and I don't want to give you the exact definition because it's clear from the picture kind of what a flip is, but it's a short talk. With this idea in mind, we can define the secondary polytope. So the secondary polytope is a polytope of dimension n minus d minus 1, where n is the number of vertices of the original polytope, d is the dimension of the original polytope, and these vertices of the secondary polytope correspond to regular triangulations of our polytope. Okay, so that's quite nice. So that tells us that the one skeleton of the secondary polytope is the subgraph of the flip graph induced by regular triangulations. Okay. Is that okay? Yeah? Yes? Can order polytopes have non-regular triangulations? I'm not sure. Oh, yeah. So every polytope admits a regular triangulation, but yeah, they can have non-regular triangulations. But I don't know how to compute those or like pick one out of my pocket or something, yeah. And so here's a picture. Here's the line segment, that's my polytope P, yeah? And this is the secondary polytope, and I can do a flip from this triangulation to this triangulation. Here's a flip connected to this flip, so there's they're connected because you could do a flip in some way from this triangulation to this triangulation and so on. Yeah. And then here's, so this is for the line segment, the pentagon, and sorry, I did this backwards. This is my polytope P. It's a square. And this is my secondary polytope. This is my pentagon, and this is my secondary polytope, which just happens to also be a pentagon. And then this is my hexagon, and then I get this nice picture. Does anybody recognize this polytope? Yeah, this is the sociohedron. Yeah. Okay. And so that's the secondary polytope. So the space of regular triangulations hasn't been studied as much for order polytopes. Okay, and so that's kind of the motivating thing for what we do. Okay. So I said I was going to shift gears a little bit. So now what I'm going to do is I'm going to talk about the order polytope of meet-irreducibles. Okay. And so I'm going to define P hat of W to be the generalized snake poset of P of W with 0 and 1 adjoined. Okay. I haven't done something crazy. I'm just taking P and I'm adjoining 0 and 1. So a maximal and a minimal element. So I'm going to say that I'm going to let Q sub W be the poset of meet-irreducibles of P hat. Okay, nothing crazy here. So by the fundamental theorem of finite distributive lattices, you know, if you took a class in numerical combinatorics, you might have done it and seen this in EC1 or something. It says that P hat is isomorphic to the lattice of filters of QW. And in this case, for our work, we order by reverse inclusion. Okay. And so this is what I mean. So this is P hat, right? It's just taking P, which is this, joining the maximal and minimal element. And then this is QW. Okay. Is everybody okay? Yeah. Any questions? I should say, what questions you should. What questions do you have? And so here, into kind of, you know, how to think about this, you should be taking P hat and removing, you know, the 1 hat element, and then every vertex which is at the bottom of a face of the Hasse diagram. So yeah, so we remove the bottom of the face of every bounded face, I guess, here, but that's not that important. So we have P hat and we have Q, which is the poset of meet-irreducibles. So now what I'm going to do is study the order polytope, not of P hat, but of Q. Okay. Yeah. Well, actually, it turns out that that's very complicated for generalized snake words in general. Okay. So what I'm going to do is I'm going to restrict myself to this subset of words V. That is the set that does not contain the substring LRL or RLR. Okay. So it becomes very, very difficult for a generalized snake poset. But in this case, we managed to get some results. Okay. So for every W in this set fancy V, every vertex of the secondary polytope is a unimodular triangulation. Okay, so that's great. I'm happy. And it turns out that every triangulation in this case is unimodular. Okay, so I'm very pleased. You know, I don't know. Maybe if you pick a polytope like out of your pocket and you ask, does it have a unimodular triangulation? I might not necessarily tell you. But now in your toolbox, you can tell them, well, they studied these and these have unimodular triangulation. So now you have examples. Okay. And again, in the same setting, we're going to let W be in this set, and we're going to let W be a word of length K. Then the canonical triangulation admits exactly K plus 1 flips. Okay. So we can tell exactly how many flips are going to happen. Are there questions? Okay. Great. And so this is a known result already, but we phrased it a little bit different. Okay. So if we take W to be the word that gives us this latter poset, and we take the poset of meet-irreducibles, then the flip graph of triangulations of the order polytope of Q is the Cayley graph of the symmetric group with simple transpositions as the generating set. Okay, that's the same thing. I'm going to look at my notes here because I always forget that detail. this is the same thing as the Cartesian product of an n simplex and a 1 simplex. And does anybody know what the Cartesian product of an n simplex and a 1 simplex is? The permutahedron. So this is telling us that the flip graph of triangulations of this polytope is a permutahedron. And the permutahedron, if you don't know what the permutahedron is, you should look it up. My absolute favorite polytope. Okay.
Andrés,
Yes.
you should start wrapping up.
Okay. Sounds good. No, I'm almost done. Okay. So twists, we define these. So any poset p hat can be kind of decomposed into ladders. Okay. So given a ladder Li, we define this this thing called a twist, which is a permutation on the set of vertices of my poset. And so we define them in this way. You know, this is a technical definition. Don't worry too much about it. But here's what I mean. And if we have our p hat, we can break these up into pieces, which are the L sub i's. And so I label them in a way that's defined here. Okay. That's a lot of terminology and stuff. So twists happen also on circuits. Okay. And from that, we can denote a subgroup of this symmetric group to be the group generated by these twists. Okay. And so this is what we call the twist group of p hat. And then elements of this twist group are called twists, and the elements lambda or tau sub I are called elementary twists. Okay. In any case, this is telling me if we look, you know, again, twists happen on circuits, so it doesn't matter if I flip first on a circuit or if I twist. Okay. So this diagram commutes. Okay, on the level of circuits. Okay, and so what else did I want to say about this? So the twist group acts on the circuits of the vertices of the polytope. And so from that, we can get this corollary that this triangulation T and this new triangulation that I obtained by twisting are two triangulations of the order polytope that admit the same number of flips. Okay. And so I think this is almost my last slide. So there's another theorem that says that the canonical triangulation of this order polytope is a regular triangulation. And for any twist, it's also a regular triangulation. So that's quite nice. So twisting preserves regularity. Okay. I'll quickly do the proof idea. So the Hasse diagram of our poset of meet-irreducibles is strongly planar. So by work of Mesaros, Morales, and Stryker, this polytope is integrally equivalent to a flow polytope. The canonical triangulation of our order polytope maps to these triangulations that happen in the land of flow polytopes, which are called Danilov, Karsynov, Koshevoy triangulations. It turns out that these DKK triangulations are regular. So the canonical so this implies that the canonical triangulation of our order polytope is are also regular. And the twist groups again acts on the canonical triangulation. So any twist corresponds to a framed triangulation in the land of flow polytopes. And by the work of Danilov, Karsynov, and Koshevoy, we know that these are also regular. And so we get this result. Okay. And so I'm about done. And so I'll end with these conjectures. Okay, so the first one is, again, if W is a generalized snake word that lives in this kind of restrictive set, we conjecture that the flip graph of regular triangulations for the order polytope is K regular, where K is the dimension of the secondary polytope. Okay. The second thing is that we conjecture that, in fact, all triangulations of the order polytope are regular. And the last conjecture that I'll mention is that the number of regular triangulations of the order polytope of the snake poset, so the snake poset that I presented very early on, not even thinking about meet-irreducibles, just the poset that's left, right, left, right, left, right, we conjecture that the number of regular triangulations is this product 2 to the n plus 1 times this Catalan number, which is kind of nice, but we have a lot of computational evidence that supports this, but we haven't been able to prove it. So you should treat this as an invitation to think about this stuff with me. And with that, I'll end. Gracias.
So we have time for a question or two.
Thank you for the lovely talk. So these special LRL and RLR that you're ignoring, is there like some higher level that's telling you why those add complexity, or do you just kind of like realize that that's like where the difficulty is?
Yeah, it's kind of by, so my advisor and his PhD students have recently gotten into a lot of computational combinatorics. And so they run all these weird experiments. And so from the experiments, I was able to notice that these were just what was happening when I could actually write something down.
Right.
And so, yeah, I don't have a bigger thing. And in fact, yeah, the complexity changes for general W. So
yeah, okay.
Yeah.
Thank you.
There was a question over here. Oh, okay. He asked it. Okay. Another questions? Okay, wonderful. Thank you. Oh, sorry, I cut it off early, but whatever. I want the coffee.